Welcome! In the Sizing and Optimization module, you will learn how to adjust the control domain's memory to optimize in-memory read caching of VMs, and you will find out about the correct CPU sizing, taking hyperthreading, vCPUs and NUMA architecture into account. I will also demonstrate the dynamic memory feature to you and discuss benefits of directly accessing hardware resources from a VM. As you have already learned, the control domain, or Dom0, is automatically configured during the XenServer installation, but depending on the amount of memory of the hardware, the control domain is configured to use more or less memory for administrative purposes. If later additional physical memory is added, the value configured during installation may be set too low and needs to be adjusted. This can easily be done using XenServer. From the server menu, select Control Domain Memory and enter an appropriate value, up to 32 GB. But note that the XenServer has to be set to maintenance mode first and requires a reboot to benefit from the new amount of memory. While adjusting the memory setting for the control domain is something that might happen to administrators now and then, adjusting the vCPU settings for the control domain is not required in normal situations and therefore not recommended. The control domain does not need pinning, that is, to have access to one or more dedicated CPUs, since it uses a special scheduler patch which ensures the control domain always has sufficient priority to work on administrative tasks, even when demanding VMs are running on the same host. If you are just curious to see the current assignments of vCPUs to the control domain, try entering host -CPU -tune blank show on the command line of XenServer. Let's talk about the CPU technology in the context of XenServer. Hyperthreading. Should it be enabled or not? This one deserves a clear yes. Enable hyperthreading. But be aware that although for architectural reasons enabling hyperthreading seems to double the amount of CPU cores, it doesn't actually double the performance. The performance gained by this feature is about 20% compared to the same system without hyperthreading. That is because hyperthreading doesn't really unlock hidden additional CPUs, but provides a way for modern CPUs to use the time in which a thread would block the CPU resources more efficient. If, for example, a thread accesses memory, which is much slower than executing CPU functions, the CPU has to wait for the memory operation to finish. Other threads are now blocked from execution. But by using the two logical CPU cores with hyperthreading, the second task can be executed while the CPU waits on the first task to finish the memory operation. Whenever you create a new VM with two or more vCPUs, you are prompted in which topology the vCPUs should be configured. A VM with 4 vCPUs can be set up to use 2 sockets with 2 cores, or 1 socket with 4 cores, and yes, 4 sockets with 1 core as well. Normally this only makes a difference for software developers, but some software might be licensed on the number of exposed sockets of the VM. In this case, saving sockets would save money. As a generic recommendation, use more than 1 socket only if needed. How many vCPUs can I assign per physical CPU core? The most cited consulting answer, "It depends," is correct for this question. To clarify this, it depends on the expected, or better, measured usage of the VMs. XenDesktop deployments tend to use more vCPUs per physical core than XenApp deployments do. If more vCPUs are allocated from a host than physical CPU cores are available, the physical CPU is called overcommitted, and some overcommitment is common practice in most virtualization scenarios, as long as the performance doesn't suffer. The diagram shows how to calculate the overcommit ratio of a host, no matter the absolute figures. A host with 8 physical cores running 3 XenApp session hosts, which have been configured to use 4 CPUs each, has allocated 12 vCPUs in total. In relation to the 8 physical cores, this host is 1.5 times overcommitted, or has a 1.5 overcommit ratio. There is also another CPU technology influencing the performance in hypervisor deployments, the non-uniform memory access, or NUMA for short. While in previous hardware generations all physical CPUs had the same, that is, uniform, access to the complete memory using a rather slow system bus, in modern hardware each physical CPU has a local high-speed connection to a part of the memory. This part is called local for a single CPU. It can still access all memory, but doing so will cost up to 30% more time than using local memory. Each CPU with its local memory is called a NUMA node. And while XenServer is fully NUMA aware, as a generic rule, the number of vCPUs assigned to any VM should stay within the number of cores available inside a NUMA node. To better understand this, take a look at the diagram. There is an exemplary hardware using 2 physical CPUs with 4 cores each, having access to 64 GB RAM in total. Both CPUs form a NUMA node with high-speed access to 32 GB. On socket 0, the control domain is already loaded using 2 GB RAM, so there are another 30 GB available. Now, 2 VMs are started using 60 GB of RAM. Since there is not enough memory to fit them both on NUMA node 1, the VMs are placed on separate NUMA nodes, so they will have the best performance. 2 6 GB VMs are then deployed. They are also deployed on separate nodes to balance the performance. At this point, there is 8 GB left on NUMA node 1 and 10 GB left on NUMA node 2. At last, one 15 GB VM is deployed, but since this VM is using 6 vCPUs, it cannot fit inside any single NUMA node, since it has more than 4 vCPUs, and must therefore span 2 NUMA nodes. This VM uses both local and remote memory resources across the 2 NUMA nodes. This can result in increased latency for memory access, which in turn leads to lower performance for this VM only. Another approach to raise performance in virtualized infrastructures is the use of pass-through technologies, as this offers 2 main advantages. At first, directly accessing functions of hardware is usually faster for any VM than having access to hardware functions managed by the control domain. And adding to this, allowing a VM to directly interact with hardware reduces load on the control domain. While it is possible for XenServer to pass through a complete PCI device with all its functions to a single VM, it is currently only supported for special graphic cards found on the hardware compatibility list, and not as a generic option for all PCI devices. Using SRIOV, the single root I/O virtualization, special hardware can expose a subset of its functions as a so-called virtual function, or VF for short, to the hypervisor. This technology is most often found with the special network adapters. XenServer discovers not only the network adapter, referred to as physical function or PF, but also the virtual functions exposed by the network adapter. These virtual functions can then be assigned in a one-to-one relationship to a VM. Within the operating system of the VM, special drivers from the hardware vendor need to be installed to use the assigned virtual function. These drivers can then access the hardware without passing traffic through the control domain or the Open vSwitch. The downside to this technology is that any VM configured to use a virtual function loses its agility. This VM is dependent on the functions of a hardware device, which is only present in a single host, and it can therefore not benefit from migration, high availability, or workload balancing. Note that network interfaces of virtual machines, which are based on virtual functions of SRIOV network cards, will not show up in XenCenter. Within XenCenter, it will seem that the VM has not been configured with a network card at all. XenServer also supports passing through GPUs, the core element of each graphics card, to VMs on a one-to-one basis. Depending on the hardware used, a graphics card can also have more than one GPU, and since XenServer assigns GPU functions to the VMs rather than the complete graphics card, multiple VMs might be effectively using a single graphics card. Configuring GPU pass-through is especially useful for virtual machines running software which demands higher graphical performance. Normally, all graphic operations are rendered on the host CPU, so assigning a GPU to such VMs not only offers higher performance for the VM, it also offloads tasks from the host's CPUs. Be aware that you can find GPUs which have been tested and are supported by Citrix on the hardware compatibility list for XenServer. Instead of passing through a complete GPU to a single VM, it might be desirable to split a single GPU so that it can be assigned to multiple VMs. It is also more efficient to use a few high-power GPUs in the server hardware than to have many medium or low-power GPUs, one for each VM. Using NVIDIA graphic cards found on the hardware compatibility list for XenServer even allows to split a GPU into vGPUs of different strength to facilitate the hosting of VMs with different graphical demands on the same hardware. This solution requires the installation of a virtual GPU manager inside of the control domain, while the actual configuration of the vGPUs and the assignment to VMs is handled by XenCenter. There are currently only 2 vendors supported by XenServer, which enable the use of so-called vGPUs or shared GPUs, that is NVIDIA and Intel. While NVIDIA uses a proprietary mechanism located on the graphics board and controlled by a management software which needs to be installed to the control domain, Intel uses the GVT-G extension of the CPU to make functions of the integrated GPU available to multiple VMs at once. This table, based on XenServer version 7.1 LTSR, helps you to decide which vendors' GPUs are supported depending on the scenario. NVIDIA offers different GPUs for use with XenServer to cater for different needs. The M6 series is, for example, designed to fit into blade systems, also with respect to thermal design. The row maximum vGPU instances in the table can roughly be translated with a number of VMs that can be assigned resources from the graphics card at once. But there is more to it. Depending on the actual GPU, a M60-based vGPU might be more powerful than a vGPU based on the M10, although the M10 can officially host more VMs in total. Also be reminded that NVIDIA allows to create vGPUs of different speed or strength from a single GPU. Note that the evolution of this technology is fast-paced, and there will most likely be different hardware generations of these GPUs already available. To use the GPUs from the NVIDIA Grid products, you need to install an on-premises license server and purchase the correct number of licenses for the intended use of the product. Be aware that there are also different licensing options regarding support and maintenance for the solution. Each VM, which has been assigned a vGPU, checks out a license from the licensing server when it is started and returns the license when it is shut down again. Purchasing the virtual workstation license as opposed to the virtual PC license enables some functions in the graphics driver which are useful in combination with image processing and construction software. The only other vendor currently supported for vGPUs is Intel. Based on their Skylake CPU architecture and chip series following this one, a GPU is available within the physical CPU, which can be split up to support the acceleration of up to 7 VMs. Although the performance of the vGPUs is maybe not as good as the NVIDIA solution, it might be enough to satisfy users' demand for acceleration of common applications like browsers or Microsoft Office, given the fact that no additional hardware needs to be purchased since the GPU is built into the CPU. To use the Intel GPU functionality, first consult the hardware compatibility list for supported versions of CPUs containing the Iris Pro family GPU. No license or licensing server needs to be used, and although the vGPU will function with a standard graphics driver on Windows, it is recommended to download and install the latest Intel video driver from their website inside the operating system of any vGPU assigned VM. To summarize the GPU options for XenApp and XenDesktop deployments, GPU pass-through assigns a single GPU per VM, so the number of accelerated VMs corresponds directly with the amount of available physical GPUs. But most vendors offer supported graphics cards for this mode. Sharing a GPU as vGPU is supported by NVIDIA and Intel and allows to base multiple VMs depending on configuration on the same GPU. And as a last option, using multi-user session hosts, any technology can be used, but all sessions of a specific host will share the assigned GPU. The dynamic memory control feature of XenServer, or DMC for short, is also known as ballooning and helps to overcome problems in situations where less memory is available on a host than required by all VMs which should be running on it. This is achieved by dynamically lowering the memory available to configured VMs in order to regain memory for other or additional VMs. To support DMC, the Xen tools need to be installed in the VM, and the administrator has to set a minimum and a maximum memory size for each VM that should be considered for this feature. DMC is a host-only feature. Memory regained on one host can only be used for VMs running on the same host. To summarize, DMC does not offer a way to extend available of physical memory in any way. It is just a redistribution mechanism for currently unneeded memory from VMs to other VMs on the same host. DMC uses a default rule set when allocating memory to machines. A VM will never use less memory than the configured dynamic minimum value, and also will never use more than the configured dynamic maximum value. Each VM will get access to the full allocated memory if enough memory is available on the host, but if not enough memory is available, then each VM will be allocated the highest amount of memory that is possible. The sum of the configured dynamic minimum value for all VMs of a host cannot exceed the amount of memory that is available for VMs on this host. And remember that the control domain and the hypervisor consume some memory as well. The table illustrates the DMC feature on a host with 180 GB available memory and VMs which have been set to require 4 GB at minimum and consume 8 GB at maximum. When only 10 VMs are running, each VM will be allowed to consume the full 8 GB per VM, since there is enough memory available. This holds true even for running 22 VMs on the same host. All VMs fit into the available RAM, but starting another VM on the host would not be possible if each VM had a static memory value of 8 GB. With 30 VMs running, each VM will be reduced by the DMC feature to a memory allocation of about 6 GB. The host's memory is now overcommitted, and running 45 VMs leaves only the required minimum of 4 GB per VM, so no additional VM can now be started on the host. Remember not to set the dynamic minimum too low, as this might increase the paging activity of affected VMs, reducing the performance of the VM, host, or the storage system. Welcome back to a short demo in which you will learn how to use the dynamic memory control feature of XenServer. I've prepared a special situation in the pool within the lab to explain the benefit of dynamic memory control, or DMC for short. My goal is to start both Windows VMs, and as you can see, each one of them is configured to allocate 4 GB RAM. The context menu of the VM shows that one host does not even have enough memory available to start this VM. The next host is currently undergoing maintenance and has therefore been disabled. So the only viable option is hype 003, but I am not going to start the VM yet. Let's take a closer look at the host's memory configuration. Out of 8 GB RAM in total, only 7 GB remain free, since the hypervisor itself and the control domain certainly need some memory too. Now it is simple math to figure out that 2 VMs requiring 8 GB each will not fit on a host which has only 7 GB RAM available, and this is where DMC can help. On the Memory tab of the VM, I choose to edit the configuration and reconfigure the VM not to use a static amount of memory, but rather a range of memory. Using the sliders or the input fields, I set the VM to require at least 3 GB, but consume up to 4 GB if enough memory is available on a host. Note that you cannot change these settings for a running VM. The context menu of the first VM now even offers to start the VM on a host that has not 4 GB available, but for this example, I want the VM to start on hype 003. You can see that the VM is currently consuming the maximum configured amount of memory, since no memory shortage exists. After logging on to the operating system of the VM, I can use the Performance tab of Task Manager to show that the VM is only using about 760 MB of the allocated 4 GB RAM. What about the second VM? This VM is not able to start since it is still configured to require the full 4 GB RAM, and even taking into account the previous configuration of the first VM, there might still be a single megabyte missing, so the VM is not able to start anywhere. I reconfigure the VM in pretty much the same way that the first VM was reconfigured. This VM is now set to also require only 3 GB at minimum, but able to use up to 4 GB if circumstances allow. To show the DMC feature in action, I explicitly start the second VM on the third hypervisor host as well, and right after the start command is issued, you will find that the first VM suddenly is only using 3 GB memory, freeing up enough memory to allow the second VM to start. Inside of the first VM, it seems like some process has all of a sudden consumed 1 GB. This is caused by a so-called ballooning process, which is instructed by the hypervisor to allocate memory within the operating system, which in turn is then lent to another VM. Note that the total amount of memory allocated to the operating system does not change. As soon as the second VM has finished booting, memory usage of both VMs start to equalize, but statistics on the host's memory tab show that this host's RAM has been over-provisioned. And since both machines have identical configuration, they will both end up sharing the available 7 GB, with each VM consuming 3.5 GB. Respectively, you will find the ballooning process inside of the VM releasing memory, which is no longer required by the hypervisor's DMC feature, so more RAM is available to the operating system again. To summarize this, DMC enables you to overcommit a host's memory in order to fit more VMs on it. While this is a good option to compensate unplanned memory shortages, for example after a hardware failure, it should, from a performance aspect, not be a generic configuration. For DMC to operate, the Xen tools need to be installed in the VM, and configuring a running VM to use dynamic memory also requires a restart. The many ways in which XenServer allows fine-tuning provide a network quality of service tuning option as well. Using XenCenter, you can select any virtual network card of a VM to access its properties. Apart from changing the MAC address of the virtual network adapter, a QoS limit can be set by specifying a threshold in kilobytes per second. This limits the rate at which the VM can send data over the configured network card, but does not limit the rate to receive data. As an example, you can use this limit for VMs which saturate the network during long-running backup or synchronization jobs. When the pool has been configured to be managed by the distributed vSwitch controller appliance, the QoS option in XenServer is not available. Use the DVSC's Web Administration Console instead. Similar to the QoS setting for the network bandwidth, there is also a setting to configure priority when it comes to access disks for reading or writing data. Whenever there is a conflict between VMs writing to a common storage repository, a scheduling mechanism takes care that all VMs or all VDI objects on a storage repository get a fair amount of time to read and write data. This feature is controlled at the VBD level, the connector object leading from a VM to its respective hard disk, but can be set for a storage repository using Linux commands as well. The default scheduler for iSCSI storage repositories, for example, is NoOp, which passes all traffic unmodified onto the iSCSI device, assuming that most storage appliances use comparable scheduling mechanisms on their own. As an alternate scheduler, CFQ could be used, lowering the total disk performance somewhat, but allocating time slices on an equal basis to each VDI object. Note that this feature only exists for LVM-based storage repositories and requires the use of the command line to change the scheduling mechanisms. Gaining higher performance is often achieved by using caching techniques, and XenServer also offers different caching techniques which can even be used in combination. The first one is called IntelliCache and is an optimization feature of XenDesktop for catalogs of virtual machines that have been created with the Machine Creation Services technology, but it requires XenServer to be configured accordingly. Machine Creation Services, or MCS for short, can rapidly provision virtual desktops based on a single base disk or golden image, which is usually stored on a shared storage repository. All VMs share this image when reading blocks from their hard disks, but will write their changes to separate diff disks. To accelerate such deployments, XenServer uses local storage to cache blocks that have been requested from the shared storage. This saves network storage traffic and reduces load on the file server, providing the base disk or golden image, which especially helps to prevent performance problems during a boot storm, that is, many VMs powered on at once. Enabling IntelliCache requires the administrator to configure XenServer to support IntelliCache, as well as to use XenDesktop Studio to enable the use of IntelliCache during the setup of the hosting connection. The configuration of XenServer to match IntelliCache needs is usually done during the installation. When prompted which format to use for the local storage repository, select to Optimize storage for XenDesktop, which will also enable thin provisioning by using X3 format instead of LVM for the local hard disk of XenServer. This step can also be performed afterwards, but would require a complete restructuring of the local storage repository on each host of a resource pool. While IntelliCache does not use memory but local storage of the hypervisor to speed up VMs based on shared storage, the in-memory read caching uses RAM resources on the hypervisor to cache storage blocks for faster access. When used together with IntelliCache, in-memory read caching holds the most recently requested blocks of any read-only VDI object in the memory of the control domain to further speed up storage response times for VMs. But in-memory read caching does not require IntelliCache to be used. It is enabled automatically for any VM which uses a read-only VDI object, which is the case for all VMs with at least one snapshot or most VMs which have been created using a custom template. Because this feature uses portions of the control domain's memory, administrators should resize the memory available to the control domain accordingly. Note that this feature is only available on licensed XenServer hosts and requires the VDI objects to be based on file-based storage repositories. To examine the impact of this feature, let's assume we need to run 4 VMs of our MCS catalog on a XenServer host, which are all based on a common base disk stored on an NFS storage repository. The first VM started requests many blocks from the common base disk, which are stored in the memory of the control domain. When the next VMs are started, they request almost the same blocks, but this time the hypervisor will deliver the requested blocks from the RAM cache. If there is a large delay between the first VM and the next VMs, or if the memory which can be used for caching purposes is not large enough, the requested blocks need to be read from the shared storage again, because the cache may have stored other requested blocks in the meantime. While both IntelliCache and in-memory read caching are technologies to accelerate MCS-based deployments of XenDesktop, XenServer version 7.1 also offers a comparable technology to speed up provisioning services-based deployments. To benefit from this feature, the PVS Accelerator Supplemental Pack has to be installed on each XenServer host of a resource pool. This enables the hypervisor host to cache the traffic between VMs and the provisioning servers, so when a target device requests blocks from the provisioning server, the respective hypervisor on which the target device is currently running can deliver the requested blocks from its cache inside the control domain's memory, provided that the requested block has already been accessed by another target device before and therefore has been cached. As you have noticed, apart from IntelliCache, all caching options require memory of the control domain to perform their function, but the memory of the control domain is sized during installation depending on the total amount of memory available, and should normally be used for administering virtual machines and coordination of resource pool functions. Since the cache operates block-based, it is sized independently from the size of the disk image or the number and size of the files on the disk image. Plan to allocate an additional 2 to 4 GB of RAM for each VDI object which needs to be cached. And be aware that the installed applications and their use can lead to huge differences in memory needed. To check the amount of memory used for caching, the Linux command free blank -m can be executed on the command line of a host. To increase the memory of the control domain, select the host in XenCenter and enable maintenance mode for this host. Then open its memory tab and click on the value beside Control Domain Memory to change the allocated memory. Note that the host has to be rebooted in order to use the new memory assignment, and do not forget to exit maintenance mode again. You have reached the end of the sizing and optimization module. Time to summarize what you have learned. We examined that contrary to the visual impression, hyperthreading does not double the CPU performance of hypervisor hosts, and you learned to consider using SRIOV technology to improve network performance or to leverage vCPU technology to raise graphics performance of VMs, potentially leading to higher hardware and licensing costs. You have also experienced how dynamic memory control allows to overcommit a host's memory, accepting some performance loss, and you know about different caching options of XenServer and how they relate to the control domain's memory.